Hello, the topic of this video is thermodynamic closed systems and entropy. And the essential question is, how do we define a thermodynamic system, and how, and eventually a little bit of the why does the energy move around inside these systems. So we have a new variable, which is going to be a really important, useful variable as we move through the rest of this unit, called thermal energy. As we mentioned before, there's lots of different letters that sometimes are used for energy, which is kind of annoying, but in this case, we'll see a capital U for thermal energy. Sometimes this is referred to as internal energy as well, so you should sort of know that those are synonyms with each other. The thermal energy of a system of particles is the sum of the kinetic energy for the particles in that system. So remember, we talked about temperature basically told us the kinetic energy of one particle. If you add together the kinetic energy of all the particles, it's going to tell you the thermal energy in the whole system. We measure thermal energy in joules, just like we would measure any kind of energy. So since temperature is proportional to the average kinetic energy of a single molecule, it's also going to be linearly proportional to U, right? If you double the temperature measured in Kelvin, you're going to be doubling the amount of thermal energy in that system. So hotter objects are going to have more thermal energy in general than cooler objects. But U is also going to be linearly proportional to N, or the number of molecules, because obviously the more molecules you have with kinetic energy, the more total energy you're going to have in the system. It's pretty easy to calculate U. It's just N, which is the number of molecules, multiplied by K, which is the average kinetic energy of the particles. Obviously, some are a little bit higher and some are a little bit lower, but since we have that average value, it's really convenient and easy to calculate. You should know this is not an equation on the equation sheet. They just expect you to understand this. But anyway, I put it down there just for fun. So if we look at some common objects and think about what kinds of things in this universe have a little bit of internal energy and what kinds of things have a lot, you know, something like a popsicle doesn't have very much internal energy because it has a low temperature, which means a low average kinetic energy, and it's not a very big thing. A mug of coffee might have the same amount of stuff in it as the popsicle, but it's going to have more thermal energy because each particle inside the coffee has more average kinetic energy than a popsicle. A glacier, you might not think of that as having a lot of thermal energy because each of the particles only has a tiny bit of energy, but there's also a lot of them, right? So even if those particles don't have a lot of thermal energy, they do have some. They are moving, okay? They're not at absolute zero. So each particle in that glacier is moving a little bit, and if you add together the kinetic energy of every particle in the glacier, you're still going to have a lot more thermal energy than you have in that cup of coffee because the glacier is so much bigger. Of course, you pick something that is both big and hot, like a volcano, and that'll have the most thermal energy of all because of both of the factors we've discussed. So a closed system is defined as a system that cannot exchange thermal energy with the rest of the universe. That means U is constant if we could make a truly closed system, or delta U would be 0. How would you make this? Well, you'd have to have a perfectly sealed, rigid, airtight box. So obviously you can't let stuff go in or out, or we're going to be gaining or losing energy that way. But you also can't let the stuff inside the box's energy change, which means no light, no heat, no other kinds of energy are being allowed to escape or enter through the wall. So that's obviously kind of a challenge. You can't make a perfectly closed system, but you can make a system that's pretty close, right? You can make a system that delta U would be extremely small or negligible in our real world. The other kind of system, of course, is open systems, and in those systems, we're going to let thermal energy move in or out, but energy in the entire universe is conserved. So we'll come back to that in a minute. So if you have two systems of energy that are coming into contact with each other, if those two systems have different temperatures, which means the average kinetic energy of the molecules in those systems is not the same, energy will move from one system to the other until they come to a new stable equilibrium temperature somewhere in between the temperatures of the two systems. Okay, so if you bring together two things that have different temperatures and you wait long enough, eventually they're going to have the same temperature, which means the kinetic energy of the molecules in both will have the same average. Okay, Doesn't mean their velocity is going to be the same or their mass is the same, but their energy would eventually come to some kind of equilibrium in between the other two. So for example, if you had a delicious cup full of ice cream and you poured hot coffee over the top of it, obviously we would start with a coffee system with a lot of kinetic energy and an ice cream system with not very much. Over the time, they will eventually meet an equilibrium in between, and then it won't matter whether it's coffee or ice cream, they're going to have the same temperature, the same kinetic energy at some point. So that means that the energy is moving from one system to the other, and the energy, the thermal energy, always spontaneously moves from the hot system to the cold system. And that means that I would never pour the coffee into the ice cream and have the ice cream steal energy, or sorry, have the coffee steal energy from the ice cream, right? We could never have the coffee grab, the ice cream has some thermal energy, but the coffee can't take that thermal energy to get hotter and leave the ice cream cooler, right? We know it's always going to go the other direction. The ice cream is going to steal the energy from the coffee instead. And we'll talk about a little bit about why a little bit later on. But there are three processes by which this energy transfer can happen. The first is called radiation. The second is called convection. And the third that we're going to be spending the most time on is called conduction. So in the process of radiation, what happens is little photons, which are pieces of light, are going to leave the particles in one of the system, and that actually reduces their total energy and their temperature. All objects radiate, which is part of the reason it's really hard to make a closed system for energy. All objects spontaneously are radiating out photons of light all the time. Light is coming out of everything all around you at every moment of the time. But the hotter the object is, the larger the amount of energy that leaves by this mechanism is. This is known as black body radiation, and we're going to talk about it a lot more at the end of the year. You know that the sun radiates light, right? So that's a good example of a black body radiator because we can see the light. It's spitting out a lot of light. So the sun is losing energy all the time. That energy is spreading out through space in the form of photons, and those photons are moving from the system of the star to other systems. They come to the system of Earth and they let us grow things and make amazing things. But people are glowing just like the star is. We're just not glowing very much. But if you use an infrared camera to take a picture, you're actually capturing the infrared photons, pieces of light that are coming off of your body. You can actually sense this with your hand. If you put your hand near there, you can feel that light coming off of your skin in the form of heat. So everybody and everything is going to radiate and lose energy by that mechanism. The second kind of heat transfer is known as convection. When systems of liquids or gases, so you want to have everything in the same state, like two liquids or two gases being combined, because there are no boundaries between those systems, the warmer and the colder particles can migrate around and they can just mix up the energy that way. So for example, if you've ever watched water boil, you know that the hot water at the bottom and the cold water at the top will mix themselves. The hot kind of convects up at the top and it carries the cold back down. It allows the whole water to come up to a temperature much faster because the particles or molecules in the water themselves can actually move. So instead of having really, really hot by the flame and really, really cold at the top, the whole thing gets kind of medium temperature. You see the same thing in a room where you have a heater and the air in the room kind of circulates. Another example is our mantle in Earth, right, is circulating. It's hotter down by the outer core and colder up at the top, but it stirs itself up and circulates. So you can see this either with systems of multiple gases or multiple liquids. So anytime you have two systems that have some kind of boundary in between them, so this may be because one of them is a liquid, the other is a gas, that's a boundary, or different types, states of matter, or you can have artificial boundaries. So like if I have a balloon around a piece of gas, that balloon keeps all the stuff in one system together, and that balloon would act as a boundary between two systems. If you have this situation, the only way those systems can exchange energy is through collisions between the molecules that are touching those boundaries. So for example, if you have a hot object on the left there and a cold object on the right, the particles at the boundary are moving too, and they're going to collide with each other through that boundary. And what's going to happen is the fast-moving particles from one side are going to hit the slow-moving particles, and they're going to speed them up. And then those particles move off and speed up other particles. Meanwhile, this fast particle lost some of its energy in that collision, so it's going to slow down. So over time, what happens is the energy, the high energy side, loses energy. The low energy side gains energy until eventually they reach equilibrium, at which point they have the same average kinetic energy or the same temperature. So over time, things are going to reach the same temperature by this process. We have a special name for energy that's moving into or out of a system through this process of conduction. It's called heat. So this is unfortunate because this is a word you've used before to mean temperature essentially, but in physics it has a very specific meaning. Heat is delta energy, kind of like work was delta energy, coming back to that later. Heat is delta energy by this process, but we use a variable to represent it, and that variable is Q. So anytime you see Q, that is specifically referring to heat that is moving in or out of a system by conduction. Heat is measured in joules, which is good because we can add it and subtract it from other joules. And another way to think about it is delta energy. So heat, because it's a change in energy, can be positive or negative or zero. Energy itself can never be negative, but heat can, because it's telling me how much the energy is changing. If you have a positive Q, that means that your system is gaining energy through conduction. And if you have a negative Q, then your system is losing energy. Of course, you could also have a delta Q, and if you had a truly closed system, your overall delta Q would be zero because the system isn't gaining or losing energy. A little bit of an aside, of course, energy is conserved, so anytime one system has a positive delta Q, that must mean some other system somewhere else has a negative delta Q to preserve conservation of energy. So there is an equation that lets you calculate the rate of heat transfer through a surface by this process of conduction. I don't love that this equation's on your equation sheet because it seems like a very specific equation for a very specific scenario, but it's on there and I wanted to make sure you guys had access to it. So if you are conducting, like you would be in that right scenario where the stove is going to conduct its energy into the pot. I don't know why I put the marshmallow on there. It's not really conduction, but anyway. You can calculate how quickly the heat is transferring from one system into another. So if you think about this, what are some of the properties of the systems, the setup of the systems that would determine how quickly that heat was transferred? I'd love for you to pause the slideshow and think about it before I tell you the answer. So what properties of that system are going to control that rate? And the answer is, number one, the difference in the temperature between the systems. So the hotter the stove is and the colder the teapot is, the bigger the difference in temperature, the faster heat is going to transfer through this system. Okay, if they're basically the same temperature, then heat doesn't want to move from one to the other. The collisions are equal from both boundaries. So the bigger the difference in temperature is one thing. The second thing is the amount of surface area in contact. So the more space we let those collisions happen, obviously is going to increase how much energy can transfer through those collisions. This is why we make teapots and burners really big. They transfer energy through more surface area that lets it happen more efficiently, lets us heat up our stuff faster. The third is something called the thermal conductivity of the material. So some materials allow energy to go through them easier than other materials. We can talk about why in class, but in general, you know that we make pots and pans out of metal because metal has a thermal conductivity that allows that temperature to transmit easily. The heat goes easily through the metal. We wouldn't want to make our pots and pans out of styrofoam because we would never heat up the water that's inside of them. And the last thing is the thickness of the material or the distance between those systems. So if that heat has to go through a really, really thick piece of material, it's going to slow down the rate of the heat transfer. So we want to have a thin material that lets that heat transfer faster if we're interested in a high rate. So the equation looks like this. Q over T, that is heat per second, okay, and that's kind of a single variable. It looks like two, but really that's a single variable. It's the rate of energy transfer by conduction, is equal to, we've got linear relationship with K, so lowercase k is this thermal conductivity of the material. So the higher the thermal conductivity, the faster the rate of energy transfer. So metals have a really high thermal conductivity. Times the surface area that's in contact, that's also linear. So the bigger the surface area, the bigger their rate. Times the difference in temperature. So the bigger the difference, the faster it's going to transfer. And then divided by L, because the thicker the material, the slower it transfers. So we have 3 linear relationships and 1 inverse relationship shown in that equation. So hopefully you're asking yourself, why is this energy moving? Why do we have heat moving from something hot into something cold? Why would it bother to do that? And it's actually a really big question, and the answer is really complicated and actually beyond the scope of this class. But there are a handful of questions that they ask about that, and they want kind of just a quick little textbook blurb answer. So the quick version of it is the reason why things and energy moves from one object to another, one system to another, is called entropy. Entropy, loosely speaking, if you haven't heard that word before, is the amount of chaos in a system or disorder. So a lot of entropy means chaos. Not a lot of entropy means very organized, orderly systems. And the same thing is true in thermodynamic systems. So if we have a system where the hot and cold are separated, we have hot on one side and cold on the other, that's considered low entropy or a lot of order. And if you have a system where the hot and the cold particles are mixed together, that's considered a high entropy system or a random chaotic system. The second law of thermodynamics says that entropy is always increasing in any closed system, even in a closed system. So this is kind of interesting. This says that every system is constantly becoming more chaotic over time, including the system of the universe. The why behind this is actually not that bad. It's a little equation, but it's not in the scope of this class, so we're not going to cover it. So for now, you just need to memorize kind of that entropy is increasing. That means that chaos or disorder is always increasing in any system, including a closed system. It is possible to reverse this process, to separate out the hot and cold particles from each other, but the work that you have to do to make that happen actually makes even more entropy in a different system. So in the universe as a whole, which is the only real closed system, we're going to have entropy always increasing. So why does this matter? Well, the reason why heat flows from a hot system into a cold system is because that is becoming more chaotic and higher entropy. The heat wants to move to a state where things are more equalized or normalized. We don't like to have heat and cold separated because of the second law of thermodynamics. So that's the why in a very short, perhaps unsatisfactory answer. Okay, last slide of the show. Your essential question was, how do we define thermodynamic systems and how or why does energy move around inside those closed systems? And I'll leave you with a little comic about what happens when we bring beautiful, ordered, crystalline objects into an ordinary, everyday school classroom. This one's always really struck me deep as a teacher. So hope you had an enjoyable slideshow. Thanks.